Assalamualaikum everyone and a very good day to all. In this video, we shall learn about the OSI model, a brief discussion on the model and comparison between TCP/IP protocol suite and OSI model will be analyzed. It will be a good understanding for you to understand better TCP/IP protocol suite and also why OSI model was not successful. Here is the table of contents for you to navigate through this video. So when people talk about internet, most will talk about TCP/IP protocol suite, but this suite is not the only suite of protocols defined. In 1947, ISO, or International Organization for Standardization, was established. ISO is a multinational body, and this kind of body dedicated to an agreement. Okay, so it is a worldwide. Almost 3/4 of the countries in the world are represented in the ISO. So ISO would do this agreement on international standards, and it also covers the aspect of network communications, and that is when OSI model comes in. And OSI stands for Open Systems Interconnection. Please do not get confused between ISO and OSI. OSI is the one is the model that we're going to learn in this video, and ISO is the Organization for Standardization. Okay, so OSI was introduced in the late 1970s. Okay, what is a open system? Open system is a set of protocols that allows any two different systems to communicate regardless of their underlying architecture. Okay, the objective of the OSI model is to show how to facilitate communication between different systems without requiring changes to the logic of the underlying hardware and software. But bear in mind, OSI model is not a protocol. It is a model for understanding and designing a network architecture. Okay, so this network architecture, we want it to be flexible, robust, and interoperable. The OSI model was intended to be the basis for the creation of the protocols in the OSI stack. In other words, the OSI model is a layered framework for the design of network systems that allows communication between all types of computer systems. In OSI model, it consists of 7 separate but related layers, each of which defines a part of the process of moving information across a network. Let's see the figure. So this is the OSI model. As you can see, there are 7 layers. We start with physical, data link, and then network, transport, and then we have 2 additional new as compared to TCP/IP protocol, session, presentation, and finally we have again application layer. The TCP/IP protocol suite was actually developed prior to the OSI model. That's why the layers in TCP/IP protocol suite does not match exactly with those in the OSI model. Okay, the first 4 layers of TCP/IP provide physical standards, network interface, internetworking, and transport function that correspond to the first 4 layers of the OSI model. But the 3 topmost layers in the OSI model, however, are represented in TCP/IP by that single layer called the application layer. Okay, as for the comparison, TCP/IP is a hierarchical protocol made up of interactive modules, each of which provides a specific functionality, but they are not necessarily interdependent, whereas the OSI model specifies which functions belong to each of its layers. The layers of the TCP/IP protocol contains relatively independent protocols that can mix and match depending on the needs of the system. Okay, so when we compare between OSI and TCP/IP models, we find that the 2 layers at the top, session and presentation, layer 5 and 6, are missing from the TCP/IP protocol suite. These 2 layers were not added to the TCP/IP protocol suite after the publication of the OSI model. Okay, so but the application layer in the TCP/IP protocol suite is usually considered to be the combination of the three layers in the OSI model. So there are two reasons of this decision of why the two layers were not added to the TCP/IP protocol suite. The first one, TCP/IP has more than one transport layer protocol. Some of the functionalities of the session layer in OSI model are available in some of the transport layer protocols. And secondly, the application layer is not only like a one piece of software. Okay, so many applications can be developed at this layer if some of the functionalities mentioned in the session and presentation are needed for any particular application. They can be included in the development of that piece of software. And as you can see here, physical and data link are typically used for underlying LAN and WAN technology. Network is internet protocol and some helping protocols. And transports, there are a few transport protocols as we've mentioned in the previous video. And finally, we have several application protocols as well. This figure shows an overall view of the OSI layers. Okay, D7 means the data unit at level at layer 7. D6 means the data unit at layer 6, and so on. So the process starts out at layer 7, which is the application layer, and then moves from layer to layer in descending sequential order. At each layer except layer 7 and 1, a header is added to the data unit. So you can also see that at layer 2, a trailer is added as well. When the formatted data unit passes through the physical layer, which is layer 1, it is changed into an electromagnetic signal and transported along a physical link. Upon reaching its destination, the signal passes into layer 1 and is transformed back into bits, and the data units then move back up through the OSI layers. As each block of data reaches the next higher layer, the headers and trailers attached to it at the corresponding sending layer are removed, and these actions appropriate to that layer are taken. Okay, by the time it reaches layer 7, the message is again in a form appropriate to the application and is made available to the recipient at the destination. So let's quickly go through all the layers in OSI. Before that, again, I want you to have your little assignment for today. I want you to create another mnemonic phrase out of the first letter, and let's again standardize by starting from layer 1 and write them in the comment down below. I think by now you should be pro in creating mnemonic, right? Okay, so the physical layer. It coordinates the functions required to transmit a bit stream over a physical medium. It deals with the mechanical and electrical specification of the interface and transmission medium. It also defines the procedure and functions that physical devices and interface have to perform for transmission to occur. So in the top right figure shows the position of the physical layer with respect to the transmission medium and the data link layer. So the major duties are physical characteristic of interfaces and media, meaning that the physical layer defines the characteristics of the interface between the devices and the transmission medium. It also defines the type of transmission medium. And the next major duties is representation of bits, which means that the physical layer data consists of a stream of bits, which is a sequence of zeros and ones without any interpretation. Okay, so to be transmitted, bits will be encoded into signals, right? In terms either electrical or optical, and the physical layer defines the type of encoding, how zeros and ones are changed to signals. We will learn more in the next chapter. Data rate is another major duty of physical layer in OSI model, meaning that the transmission rate or the number of bits sent each second is also defined by the physical layer. In other words, the physical layer defines the duration of a bit, which is how long it lasts. Okay, and last of the major duties, I mean, obviously there are more duties of physical layer, but I'll just cover this four. Is the synchronization of bits. Synchronization of bits is the sender and the receiver must be synchronized at the bit level. In other words, the clock at the sender and the receiver must be synchronized in order for them to receive correctly. Data link layer in OSI model transforms the physical layer, which is it will transform to a reliable link and is responsible for node-to-node delivery. It makes the physical layer appear error-free to the upper layer. And okay, the figure on the left, on the right, shows the relationship of data link layer to the network and physical layer. Okay, some of the major duties is framing. Okay, framing means that the data link layer divides the stream of bits received from the network layer into manageable data units, and this data units is called frames. And then another major duties is the physical addressing. If frames are to be distributed to different systems on the network, the data link layer adds a header to the frame to define physical address of the sender, which is the source address, and or receiver, which is the destination address of the frame. If the frame is intended for a system outside the sender's network, then the receiver address is the address of the device that connects one network to the next. It also deals with flow control, which is if the rate at which the data absorbed by the receiver is less than the rate produced in the sender, then the data link layer imposes a flow control mechanism to prevent overwhelming the receiver. And also the error control means that it will add reliability to the physical layer by adding mechanism to detect and retransmit damage or lost frames. It also uses a mechanism to prevent duplication of frames. Okay, error control is normally achieved through a trailer added to the end of the frame. And lastly, the access control. When two or more devices are connected to the same link, data link layer protocols are needed to determine which device has control over the link at any time. Okay, let's see an example in a data link layer. We have a node with physical address 10, sends a frame to a node with a physical address 87. The two nodes are connected by a link. And at the data link level, this frame contains physical addresses in the header, and the rest of the header contains other information needed at this level. The trailer usually contains extra bits needed for error detection. The network layer is responsible for the source to destination delivery of a packet, possibly across multiple networks. Whereas in the data link layer, previously we see that it oversees the delivery of the packet between two systems on the same network. The network layer ensures that each packet gets from its point of origin to its final destination. So that is the difference between hop to hop or node to node delivery with source to destination delivery. If the two systems are connected to the same link, there is usually no need for a network layer. However, if the two systems are attached to different networks with connecting devices between the networks, there is often a need for the network layer to accomplish source to destination delivery. So in this figure, it shows that in top figure, shows the relationship of the network layer to the data link and transport layer. The specific responsibilities of the network layer include the following, which is the logical addressing and routing. For logical addressing is the physical addressing implemented by the data link layer, handles the addressing problem locally. If a packet passes the network boundary, we need another addressing system to help distinguish the source and destination system. The network layer adds a header to the packet coming from the upper layer that, among other things, includes the logical addresses of the sender and receiver. And for routing, when independent networks or links are connected together to create an inter-network, which is a network of networks or a large network, the connecting devices, typically like routers or gateways, will route the packets to their final destination. One of the functions of the network layer is to provide this mechanism. So here you can see the difference between source to destination delivery and hop to hop delivery, where in a network we have source to source, a source to destination delivery, and for data link it is hop to hop delivery. So in the source to destination delivery, we can see that it involves more network, inter-network or large network indeed. Let's see an example in a network layer. Imagine in this figure, we want to send the data from a node with a network address A and physical address 10 located on one local area network. And we want to send it to a node with a network address P and physical address 95, which is located on another local area network. Because the two devices are located on different networks, we cannot just use physical addresses only. The physical addresses are only for local jurisdiction, meaning with the same local area network. Okay, so what we need here are the universal addresses that can pass through the boundaries of local area networks. The network or logical addresses have this characteristic. The packet at the network layer contains the logical addresses which remain the same from the original source to the final destination, which is A and P respectively in this figure. They will not change when we go from network to network. However, the physical address, which is in this case, we have 10 and 95, will change when the packet moves from one network to another. Okay, let's go to transport layer. Transport layer is responsible for source to destination or end-to-end delivery of the entire message. So let's call it process to avoid confusion with the network layer, because in the network layer, it oversees the end-to-end delivery or source to destination delivery of individual packets. It does not recognize any relationship between those packets. So it treats each one independently as though each piece belonged to a separate message, whether it is true or not. The transport layer, on the other hand, ensures that the whole message arrives intact and in order, overseeing both error control and flow control at the source to destination level. Okay, the figure on the top shows the relationship of the transport layer to the network and session layers. Um, okay, so for added security, the transport layer may create a connection between the two endpoints. A connection is basically a single logical path between the source and destination that is associated with all packets in the message. Creating a connection involves 3 steps, which we will learn more in depth later on. But basically, the steps are connection establishment, data transfer, and connection release. By confining transmission of all packets to a single pathway, the transport layer has more control over sequencing, flow, and error detection and correction. So again, let's go to the major duties. We have port addressing, okay, or some people call it service point addressing. Okay, so what does it mean is that the computers often run several programs at the same time. So for this reason, source to destination delivery means delivery not only from one computer to the next, but also from a specific process or a running program on one computer to a specific process on the other. Okay, so the transport layer header therefore must include a type of address called port addressing or port address, and the network layer gets each packet to the correct computer, and the transport layer gets the entire message to the correct process on that computer. So what does segmentation and reassembly? It is basically a message is divided into transmittable segments, okay, and each segment containing a sequence number. These numbers enable the transport layer to reassemble the message correctly upon arriving at the destination and to identify and replace packets if they are lost in the transmission. For connection control, it means that the transport layer can either be connectionless or connection oriented. A connectionless transport layer treats each segment as an independent packet and delivers it to the transport layer at the destination machine. And a connection-oriented transport layer makes a connection with the transport layer at the destination machine first before delivering the packets. After all the data are transferred, then the connection will be terminated. In terms of flow control, like the data link layer, but the transport layer is responsible for flow control of end-to-end rather than just across a single link. And for error control, again, similar to the data link layer, the transport layer is responsible for error control. However, it is performed from end to end rather than across a single link. The sending transport layer makes sure that the entire message arrives at the receiving transport layer without error, either damage or loss or duplication. And error correction is usually achieved through retransmission. So this is to show you the difference between the transport layer and network layer, where we have the location is almost the same, but the concept is slightly different, where the network layer is host to host delivery, which is also known as source to destination delivery. And for transport layer, it is the process to process delivery, because within a computer there are many different processes or programs running, so we have to be clear with that. Okay, let's go to the session layer. Okay, the services provided by the first three layers, the physical, data link, and network, are sometimes not sufficient for some processes. So this is where the session layer comes in. Session layer is the network dialog controller, meaning that it establishes and maintains and synchronizes the interaction between communicating systems. Specific responsibility of the session layer are the dialog control and synchronization. Dialog control means that in session layer, it allows two systems to enter into a dialogue. It allows the communication between two processes to take place either in half duplex or full duplex. For example, the dialogue between a terminal connected to a mainframe can be a half duplex. And then we have a synchronization. So the session layer allows a process to add checkpoints or synchronization points into a stream of data. For example, if a system is sending a file of 2,000 pages, it is advisable to insert checkpoints after every 100 pages, for example, to ensure that each 100-page unit is received and acknowledged independently. In this case, if a crash happens during the transmission of page 533, for example, retransmission begins at page 501, because the previous pages from 1 to 500 has been transmitted and need not to be retransmitted. Okay, the figure here shows the relationship of the session layer to the transport and presentation layer. Next, let's go to the presentation layer. Presentation layer is concerned with the syntax and semantics of the information exchange between the two systems. Okay, some of the responsibility of the presentation layer include translation, encryption, and compression. Okay, what does it means in transmission and translation? It means that the processes or the running programs in the two systems are usually exchanging information in the form of character, strings, numbers, and so on. The information should be changed to bit streams before being transmitted, because different computers use different encoding systems. So the presentation layer is responsible for interoperability between these different encoding methods. The presentation layer at the sender changes the information from its sender-dependent format into a common format. And the presentation layer at the receiving machine changes the common format into its receiver-dependent format. Next, let's go to encryption. Encryption is basically when you want to carry sensitive information, a system must be able to ensure privacy. So encryption means that the sender transforms the original information to another form and sends the resulting message out over the network. Decryption reverses the original process to transform the message back to its original form. And lastly, compression is when data compression, it reduces the number of bits to be transmitted. So data compression becomes particularly important in the transmission of multimedia such as text, audio, and video. Okay, let's look at application layer, the last layer in OSI model. Application layer enables the user, whether human or software, to access the network. It provides user interface and support for services such as email or remote file access and transfer, shared database management, and others. In this figure, we can see that the relationship of the application layer to the user and the presentation layer. Of the many application services available, we can see three examples here. We have X500, which is directory services. We have FTEM, is the file transfer access and management. And there's also X400, which is the message handling services. The user in this example uses FTEM and to send perhaps a file transfer. Specific services provided by the application layer include the following, which is the network virtual terminal. A network virtual terminal is a software version of a physical terminal and allows a user to log on to a remote host. Okay, so in order to do that, the application creates a software emulation of a terminal at the remote host. The user's computer talks to the software terminal, which in turn talks to the host and vice versa. Okay, the remote host believes it is communicating with one of its own terminal and allows you to log on. And then like I mentioned just now, we have FTEM. This application allows a user to access file in a remote computer to make changes or read data, to retrieve a file from a remote computer, and to manage or control file in a remote computer. In terms of the mail services, this application provides the basis for email forwarding and storage. And finally, directory services. This application provides distributed database sources and access for global information about various objects and services. So these are the summary of layers in the OSI model. You can have a look at it to summarize all that we've learned in this particular video. Okay, let's before I end, let's discuss why the OSI models was not successful. The OSI model appeared after the TCP/IP protocol suite, and most experts were at first excited and thought that the TCP/IP protocol would be fully replaced by the OSI model, but this did not happen for several reasons. Here I will only describe three, which are agreed upon all experts in the field. First one is the OSI was completed when TCP/IP was fully in place and a lot of time and money had been spent on the suite, so changing it would cost a lot. And secondly, some layers in the OSI model were never fully defined. For example, although the services provided by the presentation and the session layers were listed in a document, actual protocols for these two layers were not fully defined, nor were they fully described, and the corresponding software was not fully developed. And the third, when OSI was implemented by an organization in a different application, it did not show a high enough level of performance to entice the Internet Authority to switch from the TCP/IP protocol suite to the OSI model. So that is why it was not successful. Um, so that concludes our topic, our chapter 2, inshallah. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.